Hello, welcome to Q in Motion's course on understanding electricity and electronics devices. This is our second class, and we're going to start with a review of what we saw in our previous class. So on our previous class, we saw that current, electrical current, is the flow of charge, and it works similar to the flow of water in a pipe, right? It is measured in amps or amperes, and its symbol is a capital letter A. If we want to measure current or amps, we have to open the circuit and insert an ammeter in there. We also had a look at some prefixes for units like kilo, mega, milli, or micro. So instead of saying 0.001 amp, we're going to be saying 1 milliamp, right? So we're going to use a lot of that in this class and the following classes. So make sure you understand and you know what those prefixes mean. We also studied voltage, right? Voltage is similar to water pressure, we said. And you can think of it as the available force to move charge from point A to point B. We measure voltage in volts, and to actually measure it in the circuit, we don't have to modify the circuit at all. We connect the voltmeter between the points A and B where we want to measure, and we just measure. And that's, we take the reading, and that's it. Okay, so now let's see what is it that we're going to be looking at today. So today we're going to be looking at AC and DC, at voltage sources and resistance, resistors, and Ohm's law. All right, let's start with AC and DC. Last class, when we studied voltage, we studied that voltage is measured between 2 points A and B. And one of them is going to be positive and the other one is going to be negative. Let's say that A is positive and B is negative. If A is always positive and B is always negative, we're in what we call DC or direct current. The polarity never changes, it's always the same, right? Now, the opposite to that would be AC or alternating current. In alternating current, the polarity changes several times per second. So for instance, let's say that at some point in time, A is positive and B is negative, okay? Now, an instant later, it may be possible that A is negative and B is positive. So the polarity has reversed. And again, a few milliseconds later, A is going to be positive again and B is going to be negative again, right? And so on. And then it will change again. A is negative and B is positive. So if we plot those voltages over time, we're going to see that DC is, the voltage is constant, right? In this case, we have 12 volts constant over time. In AC, this horizontal scale is time and is measured in milliseconds, and the vertical scale is voltage, it's measured in volts. So in this AC example, voltage starts at 0 and then increases until it reaches a peak of 170 volts in about 4 milliseconds. And then by 8 milliseconds, it came back to 0 again. And a few milliseconds later, polarity reverses and it changes from positive to negative. That means if A was positive and B was negative, now A is negative and B is positive. So once polarity reverses, voltage keeps increasing until a peak of 170 volts, again negative, and then it will go back to 0. In this case, this is a cycle, right? From 0 to a positive peak, then to a negative peak, and then back to 0. So this is one cycle, and in this example, it is taking about 17 milliseconds. After this one, another cycle exactly the same is going to follow, right? And it's going to be alternating positive and negative. Now, if you do the math, right, this is one cycle and takes 17 milliseconds. This means you can fit 60 of these cycles in 1 second. So 60 cycles per second is the frequency of this AC voltage, and we call that hertz. So we refer to this as 60 hertz AC voltage. So when and where is AC and DC used? AC is used in power generation and distribution up to household outlets. So in your outlet that you have in your room, that's going to be AC. AC frequency is 60 hertz is used in North America, 50 hertz is used in Europe, and other parts of the world use either 50 or 60 hertz as well. DC, on the other hand, is used in all electronic devices and battery-operated equipment. So what happens with AC and DC when you try to measure? So multimeters can measure AC and DC voltage, and most will measure DC current, and many of them will measure AC current as well. But AC voltage and DC voltage, all multimeters will measure that, right? The thing you have to keep in mind is make sure to select AC or DC when measuring. So if you see this slide here, the selector now has two positions. One with volts and this wave on top of it, right? This is symbolizing AC. And the other one has this line with the dotted line on bottom, and this is symbolizing DC. In this case, the meter is set up to measure AC voltage, and it's indicating also on the screen, it's measuring AC. In this case, the voltmeter is connected to a household outlet in North America. So it is measuring something very close to 120 volts. In this case, 120.7 volts. Let's talk a bit about voltage sources now. Voltage sources come in different flavors. So one of the most common ones is probably batteries. Batteries, as you can see, and as you know, right, come in all kinds of sizes and shapes. So when you specify a battery, you specify a voltage, right? A simple AA or AAA battery has 1.5 volts voltage. This is a 9-volt battery, as it names says. It supplies 9 volts, and this is a watch battery. These range usually between 1.5 and 3, depending on the model. This is a smaller battery for our remote control for a garage opener, and this is a little 12-volt battery. So other than batteries, you have power supplies. This is a power supply which could be, for instance, the charger of your cell phone. And this converts AC, 120 volts AC, to a lower DC voltage here in this cable that is what you plug into your phone. And most cell phone chargers will provide about 5 volts. What you have here is an adjustable power supply. This is used in laboratories for experiments. This is actually 2 power supplies. That's why you have 2 sets of displays. The displays can indicate the voltage. So you can adjust these to any voltage you want, from 0 to probably 30 volts, depending on the model, or 15 maybe. And you have an indication of the current, right? So you don't have, if you want to know how much current a circuit is taking, you don't even have to use an ammeter. This is indicated by this laboratory power supply. Another source of DC voltage is the USB port. USB ports in computers supply 5 volts. So many times you plug stuff onto your computer USB port. For instance, you can charge your phone by plugging it to your computer port, right? So that's because this will provide 5 volts. And of course, you have the outlets that you have in your home. So what we saw is what those voltage sources look like in real life. But whenever we draw circuits and we use symbols, we don't draw the battery completely, we do not draw an outlet, we just use symbols for that. So these are the symbols that we will be using, and those are probably the most common symbols for voltage sources. This is a symbol of a battery. It represents the different plates of the batteries. The polarity is indicated here as a positive and a negative. The longer side is the positive, the shorter side is a negative. This could be indicated as simply 6 volts. You have to indicate the voltage, otherwise you don't know what the voltage is. And in this case, it's indicating 1.5 times 4. That indicates that we are getting 6 volts, but it is done with 4 cells or maybe four batteries of 1.5 volts. These two are generic voltage sources. The one on the left is a 5 volt DC source, and we know it is DC because we have a polarity indicated, positive on top, negative on bottom. It could be reversed here, but this is kind of a convention. For the most part, you're going to see negative at the bottom and positive at the top. This other symbol is 120 volts AC voltage source. And this is what you would be getting from your outlet in your home if you live in North America or some other countries that use 120 volts. Notice the wave here, right? That indicates that is AC. And of course, because polarity is changing many times per second, we cannot indicate which one is positive and which one is negative. So let's have a look at a power supply nameplate. So if you look at the power supply, this is coming from a laptop, for instance, but any power supply should have a nameplate similar to this one. Let's try to understand what is it that we see here. So the first thing we see is input voltage. It says 100 to 240 volts, and then the wave, that means AC. So remember, in the United States and other places in North America, you have 120 volts. And in Europe, you have 220, 240 volts. So this means that this power supply can be used anywhere in the world. So any voltage from 100 to 240 is going to work well here. Next thing we see is the input current. So when you plug that into the outlet, the current that's going to flow through this power supply is maximum 1.6 amps, right? So outlets are rated for a maximum current, probably 10 to 15 amps, right? Depending on the outlet. And this is 1.6 amps that's going to be taken from the outlet. So it's very, very well below the capacity of the outlet. The next thing we see is before we move to the output, it also shows that this power supply can work with 50 or 60 hertz. So again, this can be used in Europe or in the United States. So the next thing that's shown in this nameplate is the output. It shows 19.5 volts. And here the symbol for DC. So this converts from 120 volts, for instance, in the input to 19.5 in the output DC. It also shows the maximum current that you can ask this power supply to supply actually, which is 3.33 amps, right? If you try to pull more than 3.33 amps, there are two things that could happen. The power supply may overheat and make it damaged, or it's going to shut down. It's going to have some kind of current protection that's going to shut down. Most modern power supplies have some kind of overcurrent protection. So if you try to take more than 3 amps out of this power supply, this is going to shut down on you. And the last thing we can see here, over here on the nameplate, is the polarity of the plug. So if you go to the end, at the end it's going to have a plug something like this, with some connection in the center and another connection on the outside. As this is showing, the center is positive and the outside is negative. So if you connect a voltmeter here, you would connect the negative terminal over here and the positive terminal over here. Now, before we move to the next slide, I want to emphasize that the output current here is the maximum, right? 3.33 amps. Although it doesn't say here, this is the maximum current it can deliver. So if you connect these to something requiring less than 3 amps, it is okay, right? Actually, you should be connecting these to something requiring less than 3.33 amps. Otherwise, the power supply may shut down on you. Let's have a look at these two nameplates. This is the power supply, is the same nameplate we just saw and we studied in detail. And we want to connect it to this device, which says input 19 volts, 2.37 amps. So can we safely connect these two devices without damaging any of them? So the rules for compatibility are that the power supply voltage and the device voltage have to be the same or very similar at least. So what do we have here? We have 19.5 and 19 here. So those are very, very similar. So I would say from a voltage point of view, we're good to connect. The other thing we have to verify is that the power supply current has to be the same or higher than the device requirement. So this power supply can supply up to 3.33 amps. And this laptop can take or requires for operation something that can deliver at least 2.37 amps. So these two devices, I would say they are compatible. Although the voltage from the power supply is a little bit higher than the voltage required by the device, it is by a very, very small margin, half a volt in almost 20. So percentage-wise, that's almost nothing. So these two devices are compatible. You can plug them together. You can plug this power supply into this laptop, and nothing bad's gonna happen. Okay, on to our next topic, resistance and Ohm's law. So what is electric resistance? Resistance, it's the opposition to the flow of current. If we have lower resistance, that will allow a higher current, electrical current. Good conductors, for instance, have little opposition to the flow of current and therefore have low resistance. Good insulators have a very high opposition to flow of current and therefore they have a very high resistance. And resistance is measured in ohms, and the symbol is that thing that you see there, which is a Greek letter omega. If we want to make an analogy with water, the same we've been doing with voltage and current, we can have a look at these two tanks, right? So we have a tank and a pipe where water flows, and this is representing a very small diameter pipe. So the amount of water that's going to flow through here, it's very small. Now, if we have the same tank, same height, same amount of water, and we have a bigger pipe connected here, the amount of water that's going to flow through this pipe is much larger. So this is the equivalent of a low resistance pipe that allows it to flow, that allows a lot of current to flow. And this is equivalent to a high resistance pipe that only allows very little water to flow. Resistance is a property of an object, right? But it is defined by a combination of the geometry and the material. And what do I mean by geometry? Well, if the sample is longer, and longer means measured in the path where current travels, right? That will have more resistance. And if it is a sample or a device with a larger cross section or a wider device, it will have a lower resistance. And an example of this is why thicker cable is used to carry larger currents. And the other factor that is affecting electric resistance is the material of the object. For instance, a copper sample or a copper object is going to have a lower resistance than carbon. So if we want to dig a bit deeper in how in the factors that affect resistance, let's consider this piece of wire, right? This is a piece of wire of length L and area, the cross section, the surface, the area of the cross section is A. The resistance is going to be rho times L over A. You don't have to memorize this at all, but this is just to understand the factors that affect resistance. So resistance is affected by this factor rho, which is called resistivity and depends on the material. So copper will have a very low resistivity, and carbon will have a fairly high resistivity, and plastic will have a very, very, very high resistivity. And then you have L over A, where L is the length of the wire, and A is the cross section of the wire. So the longer the cable or the higher L, the higher the resistance, and the higher A or the higher the cross section, the lower the resistance. So just to have an example of what these numbers look like, a copper wire, 10 meters or 33 feet long, 1 millimeter in diameter, or that's equivalent to 0.78 square millimeters cross section, has a resistance of 0.22 ohms. So basically, if you are measuring the resistance of a wire, you will have numbers that are less than 1 ohm. Now let's talk a bit about resistors. Resistors are devices whose primary function is to insert resistance in a circuit. The question as of why you may want to insert resistance in a circuit, it may be not very obvious at this point, but we will get back to that later. But resistors are used a lot in electronic circuits and electric circuits as well. But for now, a resistor is something that whose primary function is to insert resistance in the circuit. So here we have the symbols for a resistor. It can be these two. The one on the left is more widely used in North America. The one on the right is more used in Europe. And the bottom pictures show the aspect of a resistor. If you have a look at these the resistors have a lot of different colored bands here and here. This one is a bigger resistor, so it has plus it has square sides, so the value is printed on the side. But on these ones, the value is represented by these colored bands. So let's talk a bit about these color bands and how the value is color coded there. So different colors represent numbers from 0 to 9. There's also a gold and silver, which are special colors. Resistors can have 4, 5, or 6 bands for indicating their values, but 4-band resistors are probably the most common. And on a 4-band resistor, the bands are the first 2 bands are the digit, the third one is the multiplier, and the last one is the tolerance. On a 4-band resistor, the tolerance is usually 5%, and that's represented by gold. So one of the bands is very likely to be gold, and that's your tolerance band, which is your last one. And the value of the resistor should be red, starting from the other side. So let's have a look at the color codes. You don't have to memorize these yet, but it may be a good idea if you're getting seriously into electronics. So we have different colors representing the numbers from 0 to 9. Black is 0 and white is 9. If you want to try to remember or to remember this table, black, you can consider that the absence of color, so that's going to be 0. And white would be all the colors, it's 9, so it's the highest value here. Brown is almost, it's a little bit lighter than black, and gray is a little bit darker than white. So, and the colors in the middle are the colors of the rainbow. So red, orange, yellow, green, blue, and violet. And this represents numbers from 2 to 7. So whenever these are in a digit position, remember on a 4-band resistor, there's digit, digit, multiplier, and tolerance. Tolerance, if we have a gold band in the tolerance, that's going to be 5%. If we have a digit, this is the value of the digit, and then this is the multiplier. So if we have something that is orange, 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 that is 3, 3, and a multiplier of 1K. So that would be 33K or 33 kilo ohms. If we have red, red, orange, that would be 2, 2 for the 2 digits. And then multiplier is 1K, so that would be 22K, right? So if we have a brown, black, black, that would be 1, 0, so that's 10, and the multiplier is 1, so that doesn't change. So that's 10 ohms. If you have brown, black, brown, that is brown is 1, then 0, those are the first 2 digits. So we have 10 so far, and then 10 for the multiplier because we have another brown, right? So that's going to be 100 ohms. Make sense? Now, usually not all the values are available. If you want a resistor of 335 ohms, you will not be able to purchase that. There's something called an E12 series, which is the preferred value. So these are the most common values in resistors. So this is the series. So it has the values 10, 12, 15, 18, 22, 27, 33, 39, 47, 56, 68, and 82. And this represents 12 different values. And similarly, for more precise resistors, for resistors with a tighter tolerance, there's an E24 series where you would have intermediate values here, but those would be resistors that have 5% or better tolerance. For these 12 values here, we have the colors. So 1, 0 is brown, black, 1, 2 is brown, red, and so on. So as you can see, not all the combinations are possible, right? And that makes it easier to read. When you read normal words, when you read the word series up here, for instance, you do not read the S, E, R, I, E, S letters one by one. You pretty much get, if you know the word, yeah, and you've seen it before, you just at a glance, you know what it says. Also by context, but even if you didn't have any context, you would know that series, you would know this word without having to read it letter by letter. So if you get used to read resistors, you don't have to read them one by one because these numbers that we have here are like words. Once you understand that not all values are possible or not all values are very common, you can probably read the most common values very, very easily and very, very quickly. So for instance, this one here is a 100 kilo ohm resistor or 100K. And I just know it. I see brown, black, yellow, and I know it's a 100K resistor. But if you want to check it, the brown, black means 1, 0, right? And then the yellow means that the resistor is in the 100K range. So it's that is 100K. Actually, if you go back to the previous table, the multiplier is 10,000. So this means 1, 0, and 10 times 10,000, that's 100K. If you want to go through the exercise, that's 100 ohm resistor. The following is going to be a 47K resistor. The next one, it's like a 330 ohm resistor. The next one is 100K, as I said. The next one is 22K. And the last one is going to be 1 mega ohm. And I can read those because I'm used to that. I don't have to read band by band. I just kind of know them by heart. Okay, so how do we measure resistance? Most, if not all, multimeters have a function to measure resistance, and that's the ohms function. So you're gonna find in the selector knob an ohms symbol. You put the selector knob in that position, and then you connect your probes to the ends of the resistor, and you just take the reading. And that's it. That's simple as that. But you have to be careful with a couple of things. First, it cannot be measured when the circuit is powered up. If the circuit is powered up, that will mess up your measurements. Also, to get an accurate result, you just have to measure the resistor by itself. If you have other things connected or to that resistor, for instance, if that resistor is in a circuit with something else, whatever you measure there, it's going to be a combination of that resistors with whatever else is connected there, and not just the resistor. So keep that in mind, okay? Our next topic is Ohm's law. So Ohm's law defines the relationship between voltage, current, and resistance. So R is, or resistance is voltage over current. From here, we can solve for current, which is going to be voltage over resistance, or voltage equals current times resistance. Sometimes it's represented with a triangle. So you have V on top and then IR on the bottom. The idea with this one is you can cover whatever variable you want to calculate. So if you cover the V, and that's I times R. If you cover the R, that's V over I. So if you are reasonably good with math, you can just remember one of these three equations and calculate from there. Now, something else to keep in mind is that not all devices respond to Ohm's law. So according to Ohm's law, if you put twice the voltage, you will get twice the current. Not every device responds to that. There are many that do. There are many that do that within some range, to some extent, and there are some that don't. Just keep that in mind. This is not a universal rule, but it's very important. Okay. So let's start with an example. We have a voltage of 3 volts, a DC supply, and it is applied to a 1.5 kilo ohm resistor. So what is the current flowing through the circuit? So current is voltage over resistance, so it's 3 volts divided by 1.5 kilo ohms, and that is 0.002 amps or 2 milliamps. Okay, simple enough, right? Another question. We have a motor connected to 12 volts, and when we connect that, we measure the current as being 3 amps through the motor. So what would be the equivalent resistance? We solve for R, which is voltage over current. Voltage is 12 volts, current is 3 amps, and the equivalent resistance of that motor is 4 ohms. Okay? So let's do a quick review of what we saw today. We studied AC and DC. DC is when the voltage is always has the same polarity. So the polarity is always the same, it doesn't change. In AC, the polarity changes periodically several times per second. Typically for power distribution, that's going to be 50 or 60 hertz. We also had a look at voltage sources, and for DC, the typical ones are batteries and power supplies, and for AC, that would be our household outlets. When also in a power supply, when current is indicated, it is the maximum current that it can deliver, or that it will take from the line if it is on the primary side, on the input side. And the power supply has to be able to deliver at least that the current that the device requires. So when you connect a power supply to a device, you have to make sure that the voltages are the same and that the power supply can supply at least that amount of current. And then we had a look at resistance and Ohm's law. And we saw that resistance depends on the material and the geometry of the device. The material is, some materials are good conductors and some materials are not very good conductors. So those have different values of resistance. Also, if your object is longer and thinner, that's going to be higher resistance. And if it is shorter or wider, that's going to be less resistance. And a device intended to insert resistance into a circuit is called a resistor. And lastly, Ohm's law establishes a relationship between voltage, current, and resistance with the equation voltage equals current times resistance. That is all for today. Next class, we're going to look at Kirchhoff's laws, LEDs, and switches. See you next time, and thank you for watching.